So these are only one example using Neel-Lefland theorem. You will see one more example, I mean, some more example, which is more better examples. So for that, we need to use Weyl operators, Weyl representation. So let G be an abelian group. For some reason, we need abelian group. Finite abelian group. Finite abelian group. And G hat, if it is a finite abelian group, G hat is, it's all one-dimensional. Irreducible representations are one-dimensional. And equivalently, you can consider that as homomorphism from G homomorphism from G to circle. That will give all representation, one-dimensional representation. And that is actually isomorphic to G hat is isomorphic to G. Okay? So G hat is the character. It's a group of G, that is G hat is equal to all those alpha from G to this. Okay? Homomorphism. It should be homomorphism. So this T is all those Z and C mod Z equal to 1. Okay. So then now we consider this L2G. L2G is all those functions from G to C with inner product f and G equal to summation f of G bar this G here. So maybe I will use T, f of T bar G of T. So this is the inner product and this is L2G. On this we define, so this is similar to the earlier definition we have given. We have defined Weyl operators on Cn. Cn can be considered as L2 of Zn, L2 of Zn. Okay. So we can consider Cn as like that, the usual Euclidean space. There we defined it using this group. So this is more general. We can define it more generally also with using groups. So we define for any, maybe G is not the right idea. G is using the functions. Okay, we will not be using function. We will be using only these characters. So we'll use symbol alpha, beta for this, A, B, C, D for this. Okay. So let A is in G, then you define UA. Define UA of a function. We have defined it on L2 of G. So UA of a function at T equal to f of T plus A. There's a slight difference. There we have used A inverse, I think, but this is okay. I mean, T plus A will use. I will not get confused. And also alpha in G hat, then we define B alpha. So in this case, Zn is same as Zn, and you use that. Okay? So here V alpha of F at T is equal to alpha of T, F of T. So if you see those definitions will coincide. So UA and UAF and VAF, they are unitary operators. You can easily verify. It's easy to verify. It preserves the inner product. This is translation. Translation, if you just write this inner product, you can substitute it. It's like integration. You can, change of variable kind of thing. So it's just translation. This summation is invariant translation. So if you have, so UAF, UAG is same as FG, the inner product FG. Similarly, this is just multiplying by some complex number, with modulus 1. So it's clearly unitary. So with respect of W A alpha is equal to UA V alpha is unitary. They are all unitary. When A equal to identity, you will get V alpha. When alpha equal to identity, the constant character, constant function 1, you will get the UA. Okay? So these are all unitaries. Okay? And it satisfies the following: UA V alpha is equal to alpha of A and V alpha. They don't commute, they commute up to a constant, V alpha UA. Okay. You can easily verify this on a function. Okay. If you just apply this UA, V alpha on a function, so f of t is equal to, this will be, you have alpha of t, this function, alpha of t, f of t. On this, you are going to apply UA. So this will become alpha of t plus A times f of t plus A. Okay. I mean, I'm using additive group. I'm assuming additive group. Okay. So, so this will become alpha of t times alpha of A. So you will get alpha of t here and alpha of A here, f of t plus A. So now this is just, I mean, you have alpha of t, alpha of A outside, sorry, alpha of A outside, and alpha of t, f of t plus V. So this is just V alpha acting on UA of F. That's T. So you can easily verify this same verification put there also. Okay. So it satisfies this commutation relation. So you can use this commutation relation. Okay. So, okay. I mean, we want to define a error space and we want to get a coding space. Okay. Error space are operators and coding spaces are a subspace of L2G. Our Hilbert space is L2G. Okay. So incidentally, if you have Z2, dimension 2, if you look at the Weil operator, they are precisely those Pauli operators. Okay. So Pauli matrices. Okay. Now if you have a E contained in G and F contained in G hat, you have this. Okay. Then define, you have too many definitions. Then define the error space corresponding to this to be just the linear span of, just the span of UA V alpha, okay, where A is in E, alpha is in F. That's all. Okay. You just take the span of this operator. Okay. Of course, they are not commuting when alpha has some, I mean. Okay. So, okay. So this is the error space. You want to find a error coding, I mean, some error coding space for that. Okay. Error correcting code space. Okay. So for that, let C1 contained in C2 contained in G subgroups. We take subgroups C1 and C2. Using that, we want to construct some set here. And using that, we want to construct a subspace of L2G. And that we want to prove that it is a coding space. And we want to just use Nil-Leflam theorem to verify that. That's all. So that's what we are going to do now. So assume the condition. So the condition, we call it star. Okay, we will use this condition. So star, the condition is this. So E, I am using it as additive space. So E minus V, E minus C, intersection C2. C2 is the bigger group. There are two subgroups we have. We want to construct the coding space using C1 and C2. And C2 is the bigger subgroup. So intersection C2 also is true. Is just 0. 0 is the identity. Okay? I mean, we are considering G as the additive group. So 0 is the identity. E minus E intersection C2 is 0. And similarly, a condition F inverse F. This is the character group. F inverse F. So I have to define something. I forgot to do that. So I will define that. For any subset, for any subset A contained in G, okay, you can define A per contained in A per. This is annihilator. A per contained in G hat by A per equal to all those alpha from alpha is G hat such that alpha of T equals 0 for all T in A. A can be just a set. Then A per contained in G hat is a subgroup. That is clear. if alpha t equals 0, sorry, alpha t equals 1. This is a homomorph. It's not, I mean, because annihilator I wrote 0, but this is to circle, no? So whatever goes to identity, that's what we take. Okay? Whatever alpha t equal to 1. Okay? So if alpha t equals 1 for all t, beta t equals 1, then this is point-based multiplication. The group structure here is point-based multiplication, G hat. Okay? So alpha t times G of t is also 1. If alpha t is equal to 1, then alpha inverse alpha of t is anyway 1. Okay, because that's the identity. So alpha t is 1 means alpha inverse is also 1. So if alpha beta is here, the product is there, inverse that. So this is a subgroup. So it's clearly a subgroup. Okay. So A perp is a subgroup for any set. Okay. This need not be a group. For any set, this is a subgroup. Okay. Okay. So this is the condition. So this is the condition star 1. And the condition star 2 is F inverse F. Okay. Intersection. Notice this. If A is contained in B, then B perp is contained in A perp. Okay. That is clear, because if something vanishes on a bigger set, it should vanish on a smaller set. So it's this way. The direction will be reversed. Okay. So the star 2 condition is F inverse F intersection C2 perp is contained in C1 perp. Okay. C2 perp, sorry, C which is contained, yeah, C2 is the, wait. C1 perp is contained in C2 perp is contained in C2, or C1 perp is contained in C2. So I think C1 perp is contained. No, we have C1 contained in C2, so C2 contained in C1. So intersection C1 perp should be contained in C2. That is the condition. Otherwise, there is no condition, no? I mean, C2 perp is anyway contained in C1 perp. There is no condition in that. So if this intersection C1 perp, if you take the intersection C1 perp, it should be contained in C2 perp. This is what a condition is. There is no condition for that. Okay. So these are the conditions, star 1 and star 2. So what we have is we have Weyl operators. Using that Weyl operator, we took some subset capital E contained in G, capital F contained in G hat, and script E is the span of those things. That is the error space. And this is the code to define the coding space. We use this condition. These are the two conditions. Okay. Then okay. So now we use this condition. Let S is equal to, I mean, we take the coset, one representative from the cosets of G. I mean, let S is equal to all those. I mean, it is just what is called a cross section. S contained in G be such that disjoint union of A in S, okay, A plus C1 equal to C2. Okay. This is okay. This makes sense. Okay. This is an abelian group, so it doesn't matter which way you take. Yeah. Okay. So it is just the cross section of the, you take one from each coset. Okay. So that is what is S is. Okay. Now you define C contained in L2G to be, right, P is equal to all those A in S, okay, where, I mean, this is span of this. I mean, these are functions, so this should be contained in L2G, of course. Span of this, okay, where A equal to 1, the function 1 of this A plus C1. This function. Okay, this will not have norm 1, so we can divide it by the number of elements in 1 by, this is the number of elements of cardinality of C1. If you divide this will have the same cardinality as C1. So if you divide it by that, you will get this will be, I mean, this, if you take the norm of this function, that will be 1. Sorry, it should be half because we are taking L2, no? So that should be half there. We are taking L2. So it will have a product of these two things. So it will be half. Okay? So this is Chi80. Okay. Okay. So this is the span of this. Okay? Then the theorem is with all these conditions we have written is epsilon EF error coding subspace. Error correcting code. So this C is EF error correcting code. Okay. Okay. So before before getting to that, we want to check that this Chi, these things, is an orthonormal basis. Okay. So that is clear. Let's just check it. So A and S is an orthonormal basis. I mean, they are usually orthonormal basis for C. Of course, they take the span, so you don't need to verify the span. It's orthogonal, that's what you want to say. That's clear, right? A1 to A2. So which is just summation over T and G A1 of T bar A2. And if A1 is not equal to this is, of course, if A1 is not equal to, they are going to be in this joint circle. So this is equal to delta of A1, A2. We will have 1 by, I mean, this is just to normalize that we are dividing by the cardinality effect. 1 by that we will get, and that if you sum it, I mean, you will get the cardinality, so it's clear. Okay. So this is an orthonormal basis. Okay. Number one. So what do you have to verify? The Nil-Leflam theorem says that something is an error correcting code, some subspace is an error correcting code for some error space. If you take L1, L2, I'm just recalling it, I will erase it. Even L2 in E, then we want to verify that P of L1 star L2 P is P itself, some scalar of depending on L1, L2 times P. That's what we want to get. That is the Nil-Leflam theorem. Okay. So to instead we can verify that, we can verify, I mean, we need to verify this following. We need to verify. So we want to verify that Chi A1, L1 star L2 of Chi A2 okay, equal to delta A1 A2 times some scalar, C depending on L1 and L2, which does not depend on independent of A1, A2. I mean, independent of A1 or A2. I mean, when A1 equal to A2 only, they are non-zero. So it should be independent of. That's what we want to verify. Okay. So our L1. So one thing I want to say is, if you want to verify this condition for a subspace, is enough to verify for the orthonormal. I mean, generating set. You want to verify for L1 star L2. This L1 star L2 coming from the error space, this error space, and this is spanned by this. It's enough to verify for this. Then for scalars, it's clear, right? You can take the linear combination, it's clear. So you enough to verify for this operator, this kind of operator. So if you take L1 equal to UA V alpha and L2 equal to A1 alpha 1, UA2 B alpha 2, let's verify that. So L1, L2 looks like that. Then we can compute L1 dagger L2. L1 dagger L2 is V alpha 1, sorry, L1 star. I'm using star in physics notation. It is dagger they use, so I'm getting confused with both. Okay, so if I'm using star because if I use dagger, I may get confused. So that's why I'm using star. So the right thing to use dagger only in that notation. So VA star, V alpha 1, UA1 star, UA2, B alpha 2. Okay? This is what L1 star L2 is. Okay? Now U alpha, V alpha 1 star is, so this is another thing. V alpha 1 star is V alpha 1 inverse. Okay? V alpha 1 inverse. And this star is U of minus A1. That is also by definition. From the definition you can verify. But this minus this will be V alpha 1 star U of A2 minus A1. They commute. UA1, they commute. Similarly, V alphas commute, UA's commute. Okay. So this is UA2 minus A1, and this is V alpha 2. Okay. Now you want to take this here. When you want to take this here, so this is same as alpha 1 inverse. Okay. Now when you want to take this here, if you want to take it, if you want to flip these two things, this alpha will act on this. But when you do this, it will be the other way. So you have to get the alpha inverse will act. But instead, you here alpha inverse is so alpha will act. So this is precisely alpha of A2 minus A1 times V of alpha. So it will go there. It will be A2 minus A1 times V of alpha 1 inverse alpha. Okay. Anyway, this thing doesn't matter. This is just to write it correctly. So we have got it. Now the point is, this is A2 minus A1 is in E minus E. And alpha 1 inverse alpha 2 is in F inverse F. Okay. So enough to verify this. So enough to verify, you call this condition is dagger. Okay. The condition is dagger. Maybe I will not write dagger. So enough to verify, enough to prove chi A1 U A B alpha chi A2 equal to delta A1 A2 times some constant independent. This constant will depend on A and alpha. Okay. Okay. And independent of A1. Okay. This is what we have to verify. We want to verify this inner product that UA V alpha comes. This is equal to delta, which is 0 unless A1 equal to A2. When A1 is equal to this, they will get some constant which will depend on, of course, it is a scalar only. So some scalar which depends on A and alpha does not depend on this A1 equal to A2, A1 and A2. So that's what we want to verify. Okay. Okay. So let's do that. Okay. So we have taken A1, A2 in S, okay, and A in E minus E. Okay, and alpha is in F inverse F. Okay. Alpha is in F inverse F. Okay. Now we are considering this A1, UA, U, B alpha, A2. Now this is equal to, let's just verify. These are indicator function, these are indicator function. This UA, you can bring it as U minus A here, UA star here. That will become U minus A. U minus A, see, UA of any function at t is f of t plus a. Okay. If that function is indicator function a, okay, if UA, this will be U of a minus a. It will shift the variable by a. If you look at it, if it's indicator function, it will move it by minus a. If you write that up, we have seen this the last slide. So that will be the definition. Because of that, if you bring it here, this will be summation over t in G. Okay. So 1 of, this is indicator function of a coset, okay, A1 plus T1 is a subgroup, that will be U minus A, it will be shifted by U minus A. So this will become plus A. It is supposed to shift it, it's supposed to shift the variable by minus A. So the indicator function in this, which that will be shifted by A, okay, times T. Okay. Then this will be alpha T 1 A2 plus C1. Correct. That is the inner product. Summation is the inner product. That's the inner product. We are considering inner product. The function is actually this. So that's the summation over here. This is the inner product. Okay, this is the inner product. So we want to consider the summation where this becomes non-zero. This is the summation. This is what we have. We want to see where this is non-zero. And this term is non-zero whenever there is a T is here and T is here. Okay, T should be in this. This is a set. This is a set. T should be in both the sets. Then only this term will be non-zero. Okay. So suppose if T is in, this whatever we have the summand is whatever we have the summand is non-zero for T only for, otherwise it's zero. It may be non-zero for T in this, C1 plus A1 plus A intersection C plus A2. Right? That's what it says. Okay. Now we have this A coming from E minus E. So this implies there exists X1 in C1 or T1. Let's say T1. I'm using T. Okay, T1, C1, T2 again in C1. So this is C1. Okay, C1 such that this T is equal to, this intersection has to be non-empty to start with. T should be here. So this intersection has to be non-empty. So there will exist a T1 here plus T1 plus A1 plus A should be equal to T2 plus A2. Okay. So T1 plus A plus A1 plus A should be equal to T2 plus A2. Okay. Now what do we have? We have A is in E minus. Okay. A is equal to A2 minus A1 plus T2 minus T1. So this T2, this is all in C1. Okay, this is in C1. Okay, and A2 minus A1, they are in C2 anyway. Okay, this whole thing is in C2, but A is in E minus E. Our star condition, I erased it. Okay, it was just here. Erased it. The star condition is E minus E intersection C2 is 0. It's just 0. So it has to be 0. Okay. So this is non-zero. So the summand is non-zero. Zero. Only if implies A is 0. A should be 0. Fine. For A non-zero, A not equal to 0, the summand is 0. Okay, that doesn't count. So only A equal to 0. So when A equal to 0, this inner product becomes whatever the inner product we have. This is the inner product we are considering. When A equal to 0, okay, this is just summation over T in G. A is 0. So 1 of A1 plus C1 T, okay, alpha of T times 1 of A2 plus C2 of T. Okay. Of course, this is equal to 0 when A1 is not equal to, if A1 is not equal to A2, this is going to be different cosets and they don't intersect. So this will be 0. So when A1 equal to 0, this is equal to 0. If A1 equal to A2, A1 not equal to A2. Okay. If A1 equal to A2, so we have used the A, so I use B. A1, A2 equal to B, then this inner product becomes summation over T in G. Okay. A1 equal to A2. So this is just one single thing. When A1 equal to A2, these two are same coset. So the summation will be in that coset only. So the summation will be over all those B, the summation will be over B plus C1. I'm assuming A1 equal to A2 equal to B. So the summation will be over B plus C1. Okay. And so I can assume that this is in summation is over C1, and I can have this Ts, I mean, change this T to T plus B. Okay. So this will be 1, this will be 1, this is just alpha T plus B. So this is just alpha of B times summation T in C1 alpha of T. Okay. This is what we get. I'll write it again here. So finally, we have got the inner product when A1 equal to A2, okay, and A1 equal to A2. Again, A1 equal to, I mean, and A equal to 0. A is non-zero, that is, those, I mean, the terms are 0. I mean, the summation, that the points for, I mean, the summation will be 0. Okay. So this is equal to, we have got that this is equal to alpha of B times A1 equal to A2 equal to B. Okay. And we have alpha. Alpha is in F inverse F. We have this, and we have got this summation over P in C1 alpha of P. That's what we have got. Okay. Now we have to show that this summation does not, this is a constant, of course, it is a constant, which it does not depend on B. That's what we have to show. Okay. If alpha is not an annihilator, alpha is not in C1 per. Okay. That means it's non-trivial. Okay. So you know that if you have a non-trivial character, then that sum is 0. So if, let me say this, if alpha, this is general for any group, this is a fact, which very immediately we can see. If alpha is in G hat, okay, and alpha is not equal to 1, that is, there exists T naught such that alpha, I mean, there exists some T naught, there will be exists more, alpha of T naught is not equal to 1. Okay. Then summation alpha T in G for any group G, okay, that is equal to, if you have a non-trivial character, it's not 1. So summation alpha T is equal to, you can see that summation of alpha of T plus T naught also. Okay. This is same. You can shift it, you will get the same summation only. Okay. It will just circle. Okay. So this will become alpha of T naught times summation alpha T in G times alpha of T. Okay. This just implies that 1 minus alpha T naught times whatever that summation alpha of T equals 0. But this is not 0, so this has to be 0. Okay. So if you have a non-trivial character, then this sum is 0. So if alpha is not in C1 per, that means it's a non-trivial character, that will be 0. Okay. So if alpha is not in C1, then this is equal to 0. Okay. That's what we have verified here. Okay. Now if alpha is in C1 per, okay, then we already have alpha is in, then alpha is in F inverse F intersection C1 per, which contained in C2 per is the condition 2 we have. So this implies alpha is in C2 per also, but B is in C2, alpha B equal to 1, since B is in C2. B is a coset of C1, coset of C1 inside C2. Okay. So this is alpha B equal to 1. So then this inner product will be just summation over alpha t, which is 1 everywhere. I have missed this. Sorry, I mean, in this, I have missed this. There will be this. This will be there everywhere. Okay, this constant I have missed. Okay. Now this summation, it will be sum over alpha t, where t is in C1, and this will be considered, so it will be just 1. Okay. So if when alpha is in C1 per, then this inner product is 1. Okay. Which again, it is a constant independent of B, of course. Okay. Independent of B. So that's what we want to verify. We have verified in left lump here. So this is done. Okay. Now there is another theorem. There's a better code. This is the bigger subset we can get. Okay, you just finish writing. Well, that conditions, the star 1, star 2, whatever I wrote, that is condition is just to make sure that that happens. Okay, that's all. There's nothing else in the condition. So I called it proposition or theorem, I don't know. It's theorem. Okay, we have to make a notation. We have C2 per contained in C1 per. These are subgroup, of course. So let S prime is equal to S prime be such that summation disjoint union of alpha in S prime. Okay, this is multiplication. So C2 per alpha. Okay, equal to C1 per. This is just the cosets of C2 per inside C1 per. So this is the cosets. This alpha is the cross section of that. Okay. Then define. I've used chi p of alpha. Alpha is in S prime. Okay. For alpha is in S prime, define phi alpha to be equal to 1 of, so it should be inside the group only. So 1 of C2 identity of C2 half 1 of I think it is just C2 T times alpha T. Okay, that's all. Okay. 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 Then if you have C prime equal to span of this P alpha, alpha is in S prime, okay, is again E F. The same condition. We have the same condition for E and F. Okay. Error correcting. Okay. This epsilon error. Okay, this subspace. That's what we want to do. Okay. Again, you want to check this forms an orthonormal set. Okay. This, of course, you have this cardinality of this, which you have divided by this, so this summation will be okay. So we just have to verify the. I mean, we are taking span, so we don't have to talk about generating that. We have to verify if alpha is not alpha and beta are different, then the inner product is 0. That's what you want to verify. So alpha beta in S prime then phi alpha phi beta equal to 1 by this C2, cardinality of C2, summation of 1 C2, so summation over 1 C2, so that's okay. So this will be time alpha t beta t. Okay. So alpha will come in one of that, beta t will come in the other one, right? Yeah, this is right. So this is how it is defined alpha t. If we take the inner product of this and this, alpha will come here, beta will come here, so alpha t bar beta t. So this is what you get. Okay. So and the summation is over t in t. Okay. Okay. If alpha is not equal to b, then alpha bar beta is non-trivial. Okay. It's not equal to 1. 1 in C2 hat. C2 hat itself. In C2 hat itself, not equal to 1. Wait. I mean, it could be, it could vary. I mean, no, they can both annihilate that, no? So 1 second. No, they belong to different cosets. They belong to different cosets of C2. Okay. So, I mean, we have that. If alpha bar beta, alpha, which is same as alpha inverse, that is alpha inverse. The bar is alpha inverse. Alpha inverse beta of B. Okay. So if alpha not equal to beta, okay, because they are from different cosets, because of that alpha and beta is not equal to identity on C2. I mean, yeah. I mean, otherwise it will be in C2 per. Okay. So which will I mean, they should be in different cosets, right? So that is not true. Okay. So because of that, this is equal to 0. Equal to 0. Because this is non-trivial, so sum of the character evaluated in all t in G is 0. Because of that, it's 0. And when alpha equal to that, this is 1 everywhere when you divide it by that. So this is equal to delta of alpha. So this is equal to delta of alpha. So it's an orthonormal basis for that. So this implies E alpha minus prime is Y and B. This is for, okay. We only have to verify that inner product condition for the null left hand. So that's the only thing to verify. Okay. So only need to verify, need to prove the alpha. I use beta for the other one. Okay. U, A, V, beta I can use alpha, but beta u phi alpha 2, phi alpha 1, this inner product. Okay. We want to prove equal to some delta of alpha 1, alpha 2, which is 0 when alpha 1 is not equal to alpha 2, times some constant which depends on A and beta and independent of alpha 1. Independent of alpha 1 and alpha 2. So that's what we want. Then, of course, when the condition is A is in E, and this is not set inverse, this is G minus E, okay, and beta is in F inverse there. Beta is in inverse. Okay. So let's verify this inner product. So this inner product is going to be equal to summation T in. Of course, this is one, we get 1C2 times alpha. That's how it is defined. This phi alpha is defined to be equal to some constant times 1C2 times alpha something. So this is going to be T in C2. Okay. T in C2. Okay, let's do one by one. You have to bring this UA as minus A here, and this 1 will go to 1C. So this is equal to summation. Let's say T in G itself. Okay. This has 1C2 times alpha 1 something. So this will become 1 of C2 plus A. Okay. It will become C2 plus A of T. Okay. Times alpha 1 of T. Okay, that is what when you multiply here. Okay, it will shift. No, it will shift this also. Sorry, it will shift this also. Yeah. It will shift. Yeah, it will shift to minus A. I mean, UA will become U minus A here. UA star is U minus A here. It will become U minus A here. U minus A acting on 1C2 or any set will be, the set will be shifted by A. So 1C2 plus A. But this will have alpha 1 also. This definition is this times alpha 1. So alpha 1 T minus A. That is how it is defined. Okay. This phi alpha 1 is defined by 1C2 times alpha of alpha 1 of T. So alpha is also there. That will be shifted. That will be shifted by minus A. This is right. Yeah, that will be shifted by minus A. But when you take it out, it will become bar. Okay. It will become a bar. Okay. It will become bar. Now we have V beta acting on that. So that is just beta of T times phi alpha 2 of that, which is just 1C2T. Okay. Then alpha 2 of T. Okay. So everything is counted here. Okay. There are too many things. Okay. Okay, we have this constant here, 3 constants here, and we have indicator function here. Okay. This is non-zero only if T belongs to this intersection. Okay. This is non-zero. The summand is non-zero. Summand is non-zero only, implies, summand is non-zero implies T should be in C2 plus A intersection C2. But A is in E minus E. That is, there exists x1 in C2, x2 in C2, such that A plus x1 is equal to x2. A equal to x2 minus x1. Okay. Again, the same reason. A is in E minus E, x2 minus x1 is in C2, E minus E intersection. I mean, A equal to x2. I mean, A is in E minus E. X2 minus x1 is in C2, of course. Okay. but then E minus E intersection C2 is 0. So E minus, we have E minus E intersection C2 is 0. This is our condition, star 1. So this implies A equal to 0. Okay. So A is 0. So the summand is non-zero only when A equal to 0. So we can assume A is 0. Okay. A is 0. So now this inner product is equal to A is 0. So A is 0, we get only one C2 here. So we can just sum it over only C2 and we can forget about the indicator. Okay. 1 T in C2, forget about the indicator function. Okay. Now we have alpha 1 bar T. Okay. Alpha 1 bar minus A, which is just alpha 1 of A. A is 0, so alpha 1 of A is 1. So we can remove that. A is 0, so that's gone. Okay. And we have beta T and alpha 2 of T. Okay. Which you can write it as summation T in C2, alpha 1 inverse alpha 2 times beta of T. Okay. Is okay? Okay. There we can just compose all this. Okay. Alpha 1 inverse alpha 2 beta of T. Okay. Now we know that alpha 1, alpha 2, they come from C1 perp. They are the cosets. I mean, coset representative of C2 perp inside C1 perp. Okay, so they all come from C1 perp. Okay, so alpha 1 inverse alpha 2 is in C1 perp. Okay, okay. So this is in C2. Okay, so if alpha 1 inverse alpha 2 beta is in C2 perp, suppose they are in C2 perp, okay, that is equal to 1 everywhere. Okay, C2 perp. Okay, suppose it is in C2 perp. Suppose it is not in C2 perp. Let's say, suppose it's not in C2 perp. Let us finish that case, and then we will come to the case when it is equal to C2 perp. Okay, okay, okay. We want to prove that the inner product is chi alpha 1, chi alpha 2. We want to prove that an alpha 1 is not equal to alpha 2, it is 0. When alpha 1 equal to alpha 2, you want to get a constant which does not depend on that alpha. That's what we want to prove. Okay, so this alpha 1. So suppose alpha 1, this is not in C2 perp. Okay, but then we have alpha 1 inverse alpha 2 is in C1 perp, of course. They are the coset representative. So this is in C1 perp. C. Okay. You have to use that they belong to different cosets somewhere. So is in C1 perp. Suppose yeah, if it is it cannot. No, it is in. It will not be in C. Then it will be different cosets. No, it cannot be in C1 perp. Correct. It is not in C1 perp since they are different cosets. Alpha 1 is not equal to alpha. Sorry, C2 perp. Wait. No, alpha, they are in C2 perp. They are not in C2 perp. Wait. Let's go one by one. Okay. No, I want to get that as a contradiction. Wait. No. We have C2 perp is contained in C1. C1 perp is the bigger one. Okay. So if alpha 1, so we want to, let's go slowly. Now this is in C1 per. These are cosets. So this is in C1 per. Okay. From this, I want to use the condition F inverse F. This is in F inverse F. Okay. I want to use the condition that beta in F inverse F. If I prove this is also in C2 per, then it has, this is also in C2 per, then it has to be in C, which is bigger. If it is in C1 per, that is in C2 per. So alpha 1 inverse alpha 2 is in C1 per. Okay. I want to prove, so then the product is okay, but the product, suppose the product is, okay, let's consider this case. Suppose the product is in C2 per. Let's finish this and come back to this. Okay. So suppose this is in C2 per. Okay. No, if this is not in C2 per, that will vanish. That's clear, right? Then you don't need to worry. You don't have to worry about anything. Okay. If alpha 1 inverse alpha 2 beta is not in C2 per, then this is non-trivial. This is a non-trivial character. That means it by the same argument. This is equal to 0. This is equal to 0. Okay. There is nothing to prove. So if alpha 1 inverse alpha 2 beta is in C2 per, okay, is in C2 per, we know that alpha 1 inverse alpha 2 is in C1 per. I mean, this is in C2 per, this is in C1 per. So then beta has to be, this is in C1 per, but the whole thing is C2 per, means it is in C1 per. I mean, this is in C2 per, so it is in C1 per also, which is contained in C1 per. This whole thing is in C1 per. So because alpha 1, alpha 2 is in C1 per, beta has to be in C1 per. It's a group. Okay, beta has to be in C1 per. This whole thing is in C2 per. In particular, this is in C1 per, but this is in the whole thing is in C1 per. So this has beta comes from somewhere from the air. Okay, in the bigger group G high. Okay, so beta has to be in C1 per. This implies, but beta is in C1 per intersection F inverse F, which is contained in C2 per, is the condition 2. Okay, which is in C2 per. Okay, so this implies beta is also in C2 per. Okay, so this is in C2 per, this is in C2 per, the whole thing is in C2 per. Okay, okay, now it's done. No, it will not become 0, no. I want it to become 0. So beta is in C2 per. Beta is also alpha 1. This is in C1 per. So beta is in C2 per. So alpha 1 is alpha is also in C2 per. Okay. Let me go by one. Okay. I mean, you have to remember that. Okay. The thing is the following. If alpha 1 inverse alpha 2 beta, okay, suppose, I mean, we have proved that suppose if it is in C2 per, no, what did we? Yeah, if alpha 1 inverse alpha 2 beta is not in C2 per, then that's a summation of the characters, so that is 0. Okay, so Sur orthogonality, it's called Sur orthogonality. Because of that, it is 0. Okay, now this is in C2 per. This is in C2 per. We have alpha 1 inverse alpha 2 is in C1 per. Okay, so this is of course contained in C1 per. So this implies beta is in C1 per intersection F inverse F, which is contained in C2 per. Okay, so we have that beta is in C2 per, but this is in C2 per. So this will imply alpha 1 inverse alpha 2 is in C1, C2 per, because it's a group. Okay, so this implies alpha 1 is equal to alpha. Okay, this implies alpha 1 is equal to not. I mean, we are computing when it is non-zero. It should be an alpha 1 equal to alpha. So when alpha 1 is equal, when alpha 1, so we have to consider only when alpha 1 equal to alpha. Okay, when alpha 1 is equal to alpha 2, then the summation, whatever that summation, inner product, is just going to be, so which is just alpha 1 equal to alpha 2, it is just beta of t. Okay. I mean, and beta is in C2 perp, of course, by 1 by C2. No, beta will be in, that is when alpha 1 equal, no, it is alpha 1 equal to alpha 2. Here there is no condition, there is no more condition. Okay. When alpha 1 equal to alpha 2, that whole thing, that inner product, whatever we are considering, this is just C2 times summation over T in C2 beta of T, which is a constant, does not depend on alpha 1, alpha 2. That's all. Does not depend on alpha 1, it is equal to alpha. That's what we want to verify. So we have verified nil from here. So we'll stop here.